Okay, hello everyone. Today we will learn chapter 11, linear models and estimation by least squares. Here is introduction of the linear models. Suppose we observed IID random variables y1 to yn, um, and say we also observed non-random variables x1 to xn, and we want to explain y with respect to x. We can assume that there is certain relationship between x and y, and suppose that the relationship is something like this. So here the x-axis, the observation is x, and the y-axis represent y1 to y represent y, and so this point represent the pair of xi, comma yi, and we can see some kind of relationship between x and y, which is a kind of linear relationship. Probably we can explain y with respect to x. There might be some kind of linear relationship. So probably we can model this situation like this. Y equals beta 0 plus beta 1 x. So the beta 1 is the slope parameter and beta 0 is the intercept term here. Okay, and we call y dependent variable and we call x independent variable in this situation. And also we call y equals beta 0 plus beta 1 x. This is deterministic model. We are modeling y with respect to x, but statisticians like to use probabilistic model, something like this. We want to say like expected value of y have this kind of relationship. So we are accepting small amount of error. So when we are explaining about the random variable y, there should be some kind of random thing here. So so here is kind of deterministic part with respect to x, and there's some random stuff here, and that will explain the situation why. That's our assumption in the linear model. So the modeling is something like this. Expected value, we are modeling expected value of y. So expected value of y is equal to beta 0 plus beta 1 x. And so for the given value of x, y value varies with the distributional assumption. If we assume that our epsilon follows normal distribution with mean 0 and sigma square epsilon, then probably the distribution would look something like this. Okay. Okay, let's move on to chapter 11.2, linear statistical models. So previously we explained deterministic model and say that statisticians like probabilistic model, which is modeling expected value of y. So if the model relates expected value of y as a linear function of beta 0 and beta 2, only the model is called a simple linear regression model. So we want to modeling the expected value of y. There should be a lot of functional forms, but let's think about the simplest case. If the relationship is linear function, so if expected value of y is can be only maybe in the textbook this is beta 0 and this is beta 1. There is typo. Anyway, if this is only related to two parameters, two beta parameters, we say it's simple linear regression model. And if more than one independent variable, say x1 to xp, then we can model our expected value of y. We can model this with a linear relationship, and in this case we call a multiple linear regression model. And Let me give you a simple example. If we have two two independent variables, x1 and x2, and then we will have beta 0, beta 1, and beta 2 for the related parameters, and the shape of this would look like this. Okay. And let me give you a simple question. Is expected value of, if we model some situation like this, is this a linear model? Is expected value of y equals beta 0 plus beta 1x plus beta 2x squared. So here is x squared term. But do we say this is a linear model? Actually, the answer is yes. If we specify x1 as x and x2 as x squared, and then we can re-express this like this form. So in this case, this is a linear model. And in the same way, if we replace this with the other thing, like expected value of y equals beta 0 plus beta 1 ln x plus beta 2 x square, or n plus beta 3 e to the x. Is this a linear model? And actually the answer is yes. If we can specify this is x1 and this is x2 and this is x3, this is a linear model. Um, so uh, we can express nonlinear structure with linear model as well. So this is an example of nonlinear structure, and for this kind of nonlinear structure, we can fit linear model for this kind of nonlinear structure. So yeah. Here is definition of the linear statistical model. A linear statistical model relating a random response y to a set of independent variables x1 to xk is of the form like this. And where beta 0 to beta k are unknown parameters, and epsilon is a random variable, and the variables x1 to xk assume known values. So x1 to xk are non-random known values, and we will assume that expected value of epsilon is 0, and and hence the expected value of y is equal to this thing, beta 0 plus beta 1 x1 plus beta 2 x2 plus dot 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 beta k xk. So in this case, we call this model as linear statistical model. Okay, let's move on to chapter 11.3, the method of least squares. The method of least squares is a procedure for estimating the parameters of any linear model. Suppose we wish to fit a simple linear regression model, which is this thing. So how we get estimators for this thing? So how can we get estimators for beta 0, and how can we get estimators beta 1 hat? But as a result, how can we get estimators for yi hat? This is the question that we have. So if we get estimators for beta 0 hat and beta 1 hat, that determines the linear function, this thing. So getting estimators for beta 0 hat and beta 1 hat is getting estimate for this linear function. And so these data sets are given. So we have given data sets xi, yi. Given the data sets, what would be a good way to find this linear line? One option would be minimizing the distance of these. So one option would be minimizing distance between yi hat and yi, distance between yi hat and yi. Probably sum of I equals 1 to n, and distance of yi hat and yi. And if we minimize this thing, probably we can have a good estimator for the linear line. And so the method of least square is specifying this distance with squared distance. So in a method of least squares, we are minimizing sum of squares of yi and yi hat, and so this is something that we want to minimize, and this expression can be written as this thing. And the next question is how we solve this problem, the minimizing SSE problem, and get an estimator for beta 0 and beta 1. Okay. So the problem becomes the minimizing sum of square error of this thing. So minimizing SSE with respect to beta 0 and beta 1 hat. So this function is SSE beta 0 beta 1 hat, and the xi and yi are given, and so let's look at the shape of SSE with respect to beta 0 hat and beta 1 hat. And here, if we express this, then we can see that it is beta 0 square. We have n number of beta 0 hat square plus sum of xi square beta 0 beta 1 hat square, and plus something else. And since this beta 0 hat square, this n is greater than 0, and xi square is greater than 0, so the shape, so this axis is beta 0 hat, and let this axis is beta 1 hat, and so the shape of SSE would be this kind of parabola, and so the minimum of this SSE would be this one. So the shape of function SSE can be represented like this, and minimum achieved at this red point. And so what we would like to find is to minimize this SSE, we want to find this red dot, and to do that, what we do is differentiate SSE with respect to beta 0 hat and equals to 0, and differentiate SSE with respect to beta 1 hat equals 0, then we can find the beta 1 hat and beta 0 hat at this point. So what we do is differentiate the sum of square error with respect to beta 0 and beta 1. So let's do it. So if we differentiate it with respect to beta 0, then it is integration I equals 1 to n, differentiate inside part with beta 0 hat, and that is 2 times yi minus beta 0 hat minus beta 1 hat xi, and times minus 1. This is equal to 0, and also let's derive SSE with respect to beta 1 hat, and this is to n and 2 times yi minus beta 0 hat minus beta 1 hat xi, and this time minus xi equals 0. Okay, and let's re-express these two terms. Firstly, this one. It is we can cancel 2 from here, and this side. Divide 2 both sides, and we can also make this as plus, and so now this one becomes sum of yi minus n beta 0 hat minus sum of xi beta 1 hat equals 0. And what about this part? This part becomes sum of xi yi and minus sum of xi beta 0 hat and minus sum of xi square beta 1 hat equals 0. So we have two equations, this one and this one, and we solve with respect to beta 0 hat and beta 1 hat. Then we will get the answer for this. I will explain it from next slide. Okay, so from previous calculation, let's move on to solve these two equations with respect to beta 0 hat and beta 1 hat. So from the first part, we can rewrite this as sum of yi equals sum of yi minus sum of xi beta 1 hat is equal to n times beta 0 hat. And let's move this n this side, and this part becomes beta 0 hat is equal to sum of yi divided by n is y bar, so y bar, and minus x bar beta 1 hat. Okay, so we derive this one from the first equation. And what about the second part? Second equation, let's put our beta 0 hat to here, and then what we get is sum of xi yi minus sum of xi times y bar minus x bar beta 1 hat minus sum of xi square beta 1 hat equals 0. And from here, what we get is let's solve sum of xi yi minus sum of xi. Let's write it as this way: sum of yi divided by n, and plus sum of xi square divided by n beta 1 hat minus sum of xi square beta 1 hat equals 0. And let's move this part to here, and let's try to solve these. And so if we move this part, let's see, sum of xi, sum of sum of xi, sum yi minus sum of xi, sum of yi divided by n is equal to beta 1 hat, and here we have sum of xi squared minus sum of xi square over n. And so our beta 1 hat is equal to sum of xi yi minus sum of xi sum of yi divided by n, and the denominator is sum of xi squared minus sum of xi squared over n. Okay, so we calculated beta 1 hat and beta 0 hat, and actually we can go further. Actually we can re-express this again. So let's write it this way. The upper part can be written as this: sum of xi yi minus n times sum of xi sum of yi. And actually we can plus and minus this term again. So plus sum of xi sum of yi divided by n minus sum of xi sum of yi divided by n. Okay, so this is same because this part is actually 0. And what we can do actually from here, and actually this one is x bar, so we can re-express this as minus sum of yi x bar. And actually since we have yi here and here, so we can rewrite this like this: sum of I equals 1 to n. For all yi we can xi minus x bar, we can rewrite this way. And also, what about this part? This part is plus sum of xi y bar, and what about this part? Let's see, y bar and minus, and actually for this part we can write it as n times x bar y bar. Okay, and actually this and this are the same, but anyway we can write it this way. And for this part we can put y bar outside. Then what we can do is integrate sum of xi minus x bar. We can write this way. Okay, and actually we can put y bar inside. Actually they are the same, y bar inside. So this part we can write it this way. And so for this one we can write it as this way. Since this one and this one are the same, sum of I equals 1 to n with xi minus x bar, we can take this as yi minus y bar, yi minus y bar. Okay, so we can re-express the upper part with this thing. So the beta 1 hat, the upper part we can express it as like xi minus x bar yi minus y bar. And also for the denominator part, if you put if you think yi is xi and y bar is x bar, you can similarly write this thing as this one, xi minus x bar squared. Actually, the upper part and denominator part are the same. If you put yi as xi, then the upper part and denominator part are the same. So you can similarly derive this denominator part can be written as this thing. If you are not you are not very clear about this, and then try to do this one by yourself with similar reasoning like this. You can write this part this way. So yeah. Anyway, what we derived is beta 1 hat is this thing, and beta 0 hat is this thing. Okay. And also you can solve beta 1 hat this way as well. Okay. So here's the summarized result. If you define sxy this way, this is numerator part of the previous expression that we get, and this is denominator part from the previous expression, and so beta 1 hat is this one, and beta 0 hat is this one. These are what we derived from the previous slide, so this should be clear. Before we move on to example problem from 11.3, I'd like to cover the general case first. I mean multiple linear regression case first, because simple linear regression is a special case of multiple linear regression case. And actually, the results from multiple linear regression case, it is easier to understand than the simple linear regression case for my case. So I'd like to explain multiple linear regression case first, and explain both the simple regression one and the multiple regression one. Okay, so suppose that we have the linear model of this thing, and actually this is from chapter 11.10. And so you can check 11.10 for the explanations about this chapter. Okay, so suppose we have the linear model of with k non-random independent variables. Then we can write the observation below. So we can write this way. You have y1 to yn number of dependent variables, and you can write your independent variables like this way. And here actually x0s are all 1. So this is all 1, and here x11, so this is the data matrix, and you will going to have beta, which is vector of beta 0 to beta k, and epsilon is this thing. So think about this one carefully, and then you will see that the general case of linear model can be written in this way. And if you write this way, then using the matrix form, you can write this way. The vector y vector can be represented as x beta plus epsilon. Okay. So if you think this is clear, then let's move on to how we can derive the least square estimate for beta. Okay. Here we minimize SSE beta, and this SSE beta is y minus x beta transpose y minus x beta. Okay, and actually here this is vector with size n, and this is vector with size n, and so this is vector of size n, n numbers, and also here n numbers, and if you multiply these and sum up, and that's the thing that we want to minimize. And this expression can be also written as this way: y transpose y and minus 2x beta transpose x transpose beta transpose x transpose y, and plus beta transpose x beta. And actually, to do further calculation, you need knowledge about vector differentiation, but probably you will going to learn in the future if you go to graduate school, or if you learn some of mathematical class, maybe some of professors already taught you this thing. Anyway, I will explain a little bit. You can differentiate with respect to vector beta for this sum of square error beta, and the vector differentiation, if you have so this one doesn't depend on beta, so this is, we can skip this part, and this part you have beta, and if you differentiate this thing, the result is minus 2x transpose y. So if you have beta transpose and some matrix here, if you differentiate with respect to beta, if you differentiate with respect to beta, then the result is C. And also, if you differentiate beta transpose something beta, then the result is 2 times C beta. So let's assume that you know this vector differentiation thing. Then applying this you can write this as 2 times x transpose y plus 2 times x transpose x beta, and we can write this as 0, and let's see, so this part becomes x transpose x beta is equal to x transpose y, and you can solve it with respect to beta, which is x transpose x inverse x transpose y. So this is your solution. Okay, and yeah, and so for least square estimations and solution for a general linear model, the equation is this thing and the solution is this thing. Okay, then now let's think about the simple linear regression case, which is this case. And in this case, you can specify vector y as this thing and matrix x as this thing. Then you can write x transpose x this way and x transpose y this way. And if you calculate this thing, beta hat equals x transpose x inverse x transpose y, you can check that the one you derived for simple linear regression case. So you can check it by yourself, what is beta 0 hat and what is beta 1 hat. Then you will see the calculation here and calculation here are actually the same. So Now let's move on to example problem. The first example problem from chapter 11.4. Oh, actually, chapter 11.3. Anyway, let's move on to example 11.1. Use the method of least squares to fit a straight line to the n equals 5 data points given in table 11.1. So you have this kind of data set. So if you draw your result, if this is -2, then your y is 0, -1, 0, 0, 1, 1, 1, and 2, 1, 2, 3. Okay, so you have these 5 points, and you'd like to fit the linear regression, linear line on it, and that would be y equals beta 1 hat, beta 0 hat plus beta 1 hat plus times x. This line y would be this one, and using the derivation from chapter 11.3, you have equations of these. So you first calculate sxy and sxx and put it this way, and so you can use r to calculate this thing. So you can specify yi as 0, 0, 1, 1, 3, and also you can specify xi as -2, -1, 0, 1, 2. Here your y and xi's are here, and you have n equals 5. We have 5 observations, and now you can calculate sxy and sxx. So sxy is the equation is this thing, and actually this expression can be rewritten as sum of xi yi minus sum of xi sum of yi divided by n. So I calculated this thing because this one is easier from this definition. So sxy is sum of xi times yi. So this thing is this one, and this part is this one. Okay, so you calculated sxy, and also for this part I also used the other definition for this one, that's sum of xi squared minus sum of xi squared divided by n, which is this thing, and the result, the sxy, this is 7, and sxx, this is 10. So beta 1 hat is sxy divided by sxx. So from this result you can calculate beta 1 hat, which is this one, and you can also calculate beta 0, which is this one, and the results are this thing. So your equation is y is beta 0 hat. Beta 0 hat is 1, 1 plus 0.7x. So this is the linear model that you fitted. And actually, you can solve it using the using matrix operations. And to use the matrix operation, the equation is something like this. And here, since your model can be written as this, so y equals beta 0 plus beta 1 x. And actually, to write this way, you can specify your y vector as 0, 0, 1, 1, 3, and this is same as 1, 1, 1, 1, 1. So here beta 0 times 1, and beta 1 times xi. So xi minus 2, minus 1, 0, 1, 2. And you have beta 0 here, beta 1 here. Okay, so this is the expression that you have. Y equals x times beta. Y equals x beta. Okay, and so if you write any line over here, like if you read the first line, 0 equals beta 0 minus 2 beta 1. So you can check that this expression is same as this expression. Here is y is equal to beta 0 plus this one is x and beta 1. Okay, and so we write this way, and let's try to fit our beta hat. Beta hat is this thing. So if you define this is your x and this is your y, then you can calculate beta hat. So you specify your y as 00113, and also you specify your x as you have 5 1 here and xi here. So this is our x, and you can calculate x transpose x this way, and also you can calculate beta hat, which is x transpose x inverse x transpose y, and this is our beta hat, which is this thing. So beta 0 is 1 beta 0 hat, and beta 1 hat is 0.7. So as a result, our model y is equal to 1 plus 0.7 x, and this is exactly same as the one we derived from example 11.1. Okay, let's move on to exercise problem 11.9. Information about 8 four-cylinder automobiles judged to be among the most fuel efficient in 2006 is given in the following table. So we have eight four-cylinder automobiles. So we have 8 cars and of the most fuel efficient in 2006. And engine sizes are in total cylinder volume measured in liter. So cylinder volume measured in liter. So this is engine size, and this is horsepower. And we would like to construct a linear model using this cylinder volume, the engine size, and resulting horsepower. Okay, let's move on. The number A is to plot the data point on graph paper. So you can draw the graph. This is x-axis, this is y-axis, and actually you can easily draw the graph using R. So in R, you can write your y values as vector here, and you can write x values, and simply you can plot xi and yi, and this is the data plot. And let's move on to number B. Find the least square line for the data. And to find the least squares line, you can use the formula that we learned from the chapter 11.3. You can also use the formula that you learned from 11.10. That's your choice. But anyway, in here I use this formula. And we can derive beta 1 and beta 0 this way, and using this beta 1 and beta 0, we can find the least square line for the data, which is y equals, what is beta 0? Beta 0 is 1.10 plus 56.45 x. Okay, so this is the least square line. And number C, graph the least square line to see how well it fits the data. So you can simply use R to draw the graph, which is the first line plot xi and yi, and the second line draw AB line, which is A plus BX. A is beta 0 and B is beta 1. And so you draw this graph. And let's move on to number D. Use the least square line to estimate the mean horsepower rating for a fuel-efficient automobile with cylinder volume 1.9 liter. And so if your input for X is 1.9 liter, what would be your Y? And you can easily calculate this using R, which is you can put 1.9 liter to this X, and then you can calculate your Y hat, which is this thing. Okay, so this is it. The homework for chapter 11.3 is this 11.8.